This is the screencast for section 7.4, example 3. We're going to find the length of a smooth curve again, but this time there's a catch. Remember we said that the derivative has to be defined. Well, if there's a vertical tangent within the bounds of the length of the curve is smooth, but the derivative is undefined. So we need to find a way around that. So for example here, if we were going to take and find the length of this curve for y equals x to the 1/3, that's going to be the antiderivative from -8 to 8 of the square root of 1 plus the derivative of x cubed, so, or x to the 1/3, 1/3 x to the -2/3, and then squared dx. Problem is, this derivative is not defined at x equals 0. There's a vertical tangent there. So what's going to happen is one of three things. In your calculator, you'll get a domain error. You'll have an infinite loop in your calculator, so you have to quit out of it. It will never stop. Or you'll simply get the incorrect answer. So your calculator might not even show you that you have a problem there. It might give you an answer and you don't even know that it's wrong. So how are we going to work around this vertical tangent? Well, we're going to take the inverse of the function. Now an inverse is nice because anything that's vertical changes to horizontal. Horizontal tangents don't create any errors or infinite loops or incorrect answers. The derivative would be defined there. Plus, if we're just flipping the curve over the line y equals x, that's what's graphically happening in the inverse, the length of this smooth curve stays the same. So the inverse is definitely the solution to this problem. So we need to then find the inverse. So if we have y equals x to the 1/3, I'm going to cube both sides and I get x equals y cubed. And if I wanted to graph that on my calculator, it would be y equals x cubed. But for the sake of this problem, we're going to leave it as x equals y cubed and then make this a dy problem. So first, I'm going to take the antiderivative of -2 to 2. Remember, -8 to 8 were the x values. Now we're working with y values, so I want -2 to 2. Now that's going to be of the square root of 1 plus the derivative squared, and then yes, that's a dy problem. So now what is the derivative of this function? Well, that's just going to be 3y squared. So now I can simplify a little bit and integrate with my calculator, and I get 17.26 units, which makes sense. From the distance, the straight distance between -8 and +8 on the x-axis would be 16. A little bit curvy would be 17.26. The now try problem number 25 says find the length of the curve. So f of x equals x to the 1/3 plus x to the 2/3 between 0 and 2. Well, if I'm going to find the length of the curve, it's going to involve finding the derivative, so I need to make sure the derivative is defined everywhere. So the derivative is 1/3 x to the -2/3 plus 2/3 x to the -1/3. So again, actually neither term here is defined at x equals 0, therefore the derivative is not defined at x equals 0, so I have to take the inverse. Alright, well before I start the mess of the inverse, because trust me, it's going to be a mess, I'm going to first find the lower limit of integration by plugging in 0 to the function to find out what y value I need to plug in, and that turned out to be 0. Then I'm going to plug in 2 for the x value to find out what y value. That y value cannot be simplified, so I'm just going to say it's going to be the antiderivative from 0 to now 2 1/3 plus 2 2/3, the y value that comes along with when x equals 2, of the square root of 1 plus the derivative of the function squared, and this is going to be a dy problem. Alright, so let's find the inverse. I'm going to start out with y equals x to the 1/3 plus x to the 2/3. Well, trying to think of a way to algebraically combine those, basically trying to solve for 1x here, and I can't think of a way. Now I do see that this is x to the 1/3 plus x to the 2/3, so you know what, I'm going to subtract y from both sides and rearrange that. X to the 2/3 plus x to the 1/3 minus y. Now this may look very unfamiliar to you, but here's a nice new tool you can put in your algebra box. This is actually quadratic. How this is happening is 0 equals x to the 1/3 squared plus x to the 1/3 minus y. So you have a squared, a single exponent, and a 0 exponent. In other words, you have 0 equals 1 x to the 1/3 squared plus 1 x to the 1/3 to the first, and then minus y, x to the 1/3 to the 0. So this quadratic isn't solving for x equals the opposite of b plus or minus the square root of whatever. It's actually solving for x to the 1/3 equals, because x to the 1/3 is kind of like our u. It's 1u squared plus 1u minus y with no u's. So our a, b, and c coefficients are 1, 1, and negative y. So I can use quadratic formula with those coefficients. Remember, y is weird. It's a variable, yes, but it's also the coefficient of what I'm solving for using the quadratic formula here. So now I get this expression for x in terms of y. I'm going to simplify a little bit, and then remember I'm solving for just x. So I'm going to cube both sides, and I get that, well, the 2 in the denominator turns into a 1/8 after it was cubed. And then negative 1 plus, we don't need to worry about the minus version because we only want the x values between 0 and 2. And then the whole expression here cubed, the numerator basically cubed. So now I have the function, the original function, solved for x using this bizarre quadratic system. Well, we're not done. That's not what you plug in here. We plug in the derivative. So let's take the derivative. X prime equals, well, I've got the 1/8 as my coefficient. I'm going to drop the 3 down as the new coefficient with the 1/8, and now my exponent is 2. Now I'm using chain rule here, so here's the derivative of the inside. Derivative of negative 1 is 0, and then this square root is a 1/2 power, so there's the 1/2 as a coefficient. Now that little quantity is to the negative 1/2, and now I got to take the derivative of the inside and multiply by that, so that is 4. Again, what a mess. I can simplify a little bit, but this isn't going to get pretty. So instead, I don't ever want to write this expression out again. I've got this on my piece of paper. So now all I need to do, I've labeled this x prime. I can tell my grader I'm putting x prime into my formula. And now I can use my calculator and solve, and I get 3.614 units. Again, this makes sense. A straight distance between 0 and 2 is 2 units, so it's going to be more than that, 3.614 units.